Welcome to the blockchain meetup Basel.
Who here actually has heard about blockchain? Well, I guess most of you, because you've read the title of this meetup. Who here owns Ether or Bitcoin? Okay, cool. So we have some people, like half the people here, who are familiar with what blockchain is, I hope. I mean, you can also buy Ether or Bitcoin without knowing what it is. It's like, you know, trading like some rare art without knowing what art is. You can do that, but it's maybe not the best idea. So in any case, I'm aiming at giving an introduction to blockchain into smart contracts, and then in the second half do some interactive thing with you. So to see this stuff in action. But let's start real simple. We will start with a thought experiment, or as what's termed in a time when the German-speaking area was still kind of at the forefront of scientific discoveries, a Gedankenexperiment. And that's what we're going to do tonight. So we will just envision a blockchain, and we will just draw a mental picture which gets closer and closer to what a blockchain really is. Okay? And we will get to a stage where we kind of transition then to a real blockchain and demo that one. So we will start our thought experiment with a very simple aim. We will log financial transactions. And that's really very simple, but that's what many financial institutions do actually at their core. So we have transactions on a numbered account. So we have some recipient and some sender and some recipient, between which we exchange some value. So you could see that as a Swiss franc transaction. So it doesn't have anything to do with blockchain yet. We're just kind of trying to find what we're solving here. So, and many banks work great on that, right? And make tons of money, and the system, looking at it from the outside, seems to work pretty good. But it also comes at a cost. And the cost is that the IT infrastructure that you run beneath it just to facilitate this very simple exchange of value is actually very costly. It's costly or almost impossible to upgrade, and there's a whole branches of industry that are just grown around this very simple problem. And it works, but it comes at a cost, right? And one problem is technically expressed mutability. So it is the problem that we don't have any inherent security against a hacked database in which we log these transactions. So it doesn't matter really how we store that. It could be a text file, a SQL database, an Excel sheet, NoSQL database, whatever. Whatever your asset is, you have to protect it. And that is, of course, possible, but it's not inherently possible, right? So if you have an Excel sheet, you need to store it somewhere, you encrypt it somehow. Still, you want to have it updatable and accessible. And these two things are kind of usually mutually exclusive. And what we're going into now is how we can provide an inherently secure database which we can use for the exchange of financial value. Okay? And one issue, of course, is one example of what can go wrong here is if, let's say, I'm admin of this database and I say, I didn't receive a certain number, I received a bit more, right? I just say, okay, I got a bit more here. And that is fundamentally what we have to defend against. So even if it sounds like a very much a toy example, this is at its core what we really have to defend. And it gets worse if we say we don't just have one Excel sheet, but we actually have many, right? And if our thing grows. And it gets even worse when we say we combine it with a peer-to-peer network. So if we were to say we have many computers that are spread across the globe that all serve some sort of a database. Now, we actually have that, right? So we have kind of databases and we have peer-to-peer networks. I assume most of you know, for example, the torrent network, which we use to exchange secure copies of our movie collections, right? So this network is a peer-to-peer network. Now, why would you not use that really as a means to download such a database? Because it's just difficult to really make sure that what you get is what you think it is. So if you download executables, if you download some programs, you will know that you better don't take those which you got from some torrent because there's a virus behind it, right? And that gives you a feeling, again, of this mutability. So you have this program, and if you download it as a torrent, you don't know what is really behind it. And the same thing applies to our toy example of financial transactions. So let's assume we have these machines here. So we have 5 computers somewhere on the planet, and there's a new one joining. And this new one now has the problem. So this one is joining here, and we would like to know, this is Alice's laptop, by the way, and Alice wants to know which data to trust. So I'm downloading this log of financial transactions from all these machines. You can say, hey, I downloaded from all these machines. I compare them one by one, and then kind of I know pretty much where I am. But this is a bit complex, and it's actually a very difficult task as to at what time can we trust which state of our database, of our financial log sheet. And what I'm going to propose here is actually a bit counterintuitive at first, but it basically serves this issue. Which data in this globally distributed database can we trust? So what we're going to do first might not be very intuitive, and that is batch processing. It's also not something very exotic because it's something that is done in any sort of banking system. So any sort of financial banking systems do batch transactions. So you have some transactions coming in, and you say, for example, here the first 3 come in like one after another, so we batch them together in a block. This is also nothing really unheard of. It might not be obvious because it doesn't actually make things better, because instead of 1 table, we now have 3, right? So we have 3 times this header, and the slide is already much more crowded, so what's the point? What we're going to do here is that with these transactions, which come in sequential order like this, we're actually chaining together. Okay, so how does this actually work? So we have block number 1, where we said, okay, we have these transactions, and we want to chain all these different transactions together so that we can always know retrospectively what was known by everyone in our network. We're talking about this global peer-to-peer network for the exchange of exactly this database sheet here. Okay, how do we do this? Well, what we're going to do is that we calculate a fingerprint of this first block of transactions. So we have these first 3 transactions, and we now calculate a unique fingerprint. And what we're going to do here is that we calculate the digital root, in German Quersumme. Okay, so we just add up all numbers. So every single digit that you see here, we add up. So 1 plus 2 plus 1 plus 5 plus 3 plus 1 plus 1 plus 0, and so on. We get 21, and 2 plus 1 is 3. Okay, so 3 is our fingerprint of the first block. Now this one, this fingerprint of this first block, is incorporated in the header of the next one. So we have this number 3. And we repeat the same exercise as before. Now in this exercise, we importantly include this number 3. Okay, so we include this number and do this exercise again. So we add it all up and get to the number 5. Now in the next block, we incorporate this number 5, and so on and so forth. And in this way, just by incorporating this link to the previous block, just by incorporating this fingerprint, we've actually chained all these block of transactions together. Now what happens if we were to cheat here again? So what happens is that our chain is broken. Okay, we have this 10, and I again pretend, hey, I actually got 5,000, and what happens here is not just this fingerprint, but also all following ones break, right? So we broke our chain, and if we want to know, if I get data from all of you guys, and I want to know if any one of you kind of messed with the data structure, the only thing I need to compare is this latest fingerprint. I only need to compare that part and know if we are all on the same page. Okay? Now, there's a problem here, right? Can somebody tell me what can go wrong here? Yes?
You can change a block and still get the same fingerprint for this block. If you just add 9 and 1
Yes, so if, for example, yeah, 1 and 9 not, right? Because 1 and 9, then we have one more.
Yeah.
We told some...
Add some
Yeah.
zeros.
Yeah, add some
Yeah,
zeros,
zeros.
right? Yeah. So, yeah, that's actually...
Like 10,000, yeah.
Yes,
Yeah.
he knew it. He was the cheater. Right? So,
I'm from insurance.
okay. Of course, right? Of course. Don't trust the centralized institutions, right? That's the message here. So,
We sell insurance.
Yeah.
That stuff. No, not really. But that's
But maybe
what insurance
soon.
is about.
maybe soon. Who knows? So, instead of buying an insurance, what can we do to really solve this problem here? We don't, well, what we had here in our toy example was a very stupid function, right? We used this cross sum, which is not exactly a good function, to calculate a fingerprint off. So we have to solve this problem. There will be a short side note on how we solve this particular problem. And what we're going to do is these so-called hash functions. And a hash function is really a function that you can put any sort of input in. So any sort of arbitrarily sized input you put in. And what you get out is something like this here that has a constant length and has a couple of nice properties which we're going to use extensively in any sort of blockchain design. So you're over and over hearing about these hashes. So I just want to give you a fundamental understanding of what a hash function actually does. So it's a function, as we said, where you could put any sort of message in. For example, we can put in our entire block, right? All these transactions with all these numbers we can put in. And on the bottom, we get out something like this. Now, this is basically an analogy, right? So this is Meher, and Meher has a fingerprint. And in the same way, yeah, we can only deduce from Meher. We can take Meher's finger and get the fingerprint. But unless we have a database, we can take the fingerprint and know, okay, this is Meher. I don't know, right? If I see a fingerprint somewhere here on the table, I don't know that this was Andre. So it only goes in one direction. And that is important. So you cannot deduce it in the other way. And the same goes for data, of course. We can use some input, we calculate a hash, and we can't really go in the opposite direction. Now, another property that is pretty important is this collision resistance. So what does collision resistance really mean? It means that if we take Meher and his fingerprint, you can't find a second person like me that has the same fingerprint, right? We all have different fingerprints, else it would not be used for biometric identification. I mean, ideally.
It's improbable.
It's improbable.
It's possible.
Right, right. So mathematically, it's all not correct what I say here, okay? I forgot to mention a disclaimer. So it's improbable. It's actually mathematically quite probable that there is such a thing, and hence actually a fingerprint is a terrible means of securing anything really, but yeah. So yeah, this is actually an important analogy, because it is with the hash functions that we use here in blockchain space, it is so improbable that for the functions that is most commonly used, there's not a single known collision node. So there's not a single input and a second input that produce the same hash. And that's despite the fact that there's billions and billions of hashes calculated every single second. So it's quite improbable that two inputs have the same output. That's kind of one important property of these hash functions. All right, so with that little side note, we go back here to our toy example, and instead of incorporating the cross sum, we incorporate the block hash, right? We incorporate the hash of this previous block. So we take all this data, we calculate the hash, and we get something like this. Then in the next block, we take all this data, including this block hash here, we calculate the hash out of all of it, and we get this one here, and so on and so forth. So in a very simplistic way, this is how we could simply compare the latest block hash and know that we are on the right track of the data. And we are all in the same state of the database. Now, yeah, if we try to cheat in this example, despite just adding some zeros here, we totally change and mess up this block hash. So we have a very easy way of ensuring that everyone in this database is kind of on the same page. Now, that's what we call inherent validity, that changes in one block invalidate all following blocks, right? So do one change up there, and it ripples down the entire chain, and it all blocks that follow it are being invalidated. Now, that's nice, but how do you actually use that, right? What comes next? So we go back to our peer-to-peer network, and now that we have this database, we have all these people inside this database. All of them store their ledger, so their database. If you call it ledger, database, Excel sheet, doesn't really matter. And we can now be sure that Alice joined and everything is good, so we know that we're all on the same page. But how here in this example can we actually make sure that when she sends a transaction that this is correct, right? So first of all, let's look at the fundamentals. What does it mean to, if we use this as a financial logging sheet, how can we actually send money from A to B? Let's take the example where Alice wants to send 10 Ether. So Ether is just one currency in such a network called Ethereum, but there are many others. So it's just a denomination just like the Swiss franc is. So CHF for Switzerland and Ether for the Ethereum blockchain. So what actually happens if you send a transaction, you don't just send it to Bernard, you send it to everyone in this entire network. And everyone then updates their ledger and appends it to the list of transactions and to the list of updated accounts. So instead of Alice just sending something to Bernard, she shares it with the entire network. Okay, that's first one fundamental understanding of how transaction in the blockchain really works. But now the problem is, how does Bernard and actually all other participants in this network know that this transaction actually comes from Alice? That's kind of not so clear, right? Because it could be that it's just me sending this stuff. And what's happening here is that we utilize something that's called a digital signature. And digital signature is also nothing new. It's been around for quite some time and it's used in a number of fields. And it basically just takes this message, 10 ETH to Bernard. It combines it with a private key that is treated as a secret, so you don't give it out to anyone else. With this, we sign this transaction, 10 ETH to Bernard. And Bernard then, and this is interesting, has the possibility to verify it. How can Bernard verify it? He needs a so-called public key. So these two are related, right? So there's one private public key that Alice keeps very secret, and one that she gives out, right? I give this out to you, and you can verify that really this transaction comes from me. That's just one very elegant way of saying, okay, nobody messed with this stuff. So it could be that nobody wants to broadcast it in the worst case, but nobody can really interfere with the data. Nobody can really change and say, hey, you know, it was actually 5,000. Like this can just not happen because you see the digital signature that is associated with a certain message. Now, how do these things fit together in our simplistic toy example? Let's look at what we do. So what we do is we simply append another field here in our toy blockchain. We call it signature, right? So we add this signature here, and this is the signature for all this stuff, right? It means that all this stuff here is signed, right? Just like a handwritten signature. The problem is now, how do I verify it? How do I actually verify that this signature is really coming from here? And the solution is actually quite elegant, that the public key is kind of an address. So this from field is actually the public key that I use to verify this transaction. So it's a very elegant way of actually putting all these things together. So we have a signature that it comes from here. So every sender equals a public key. For some blockchains, there's some steps in between, but basically that's what it is. And we can use that to verify that this stuff here has not been altered. This has not been attacked in between. And this is kind of, again, keep always in mind the setting of a globally distributed database and set of transactions in between. Okay? Good. There is a bit the problem, where does this public key actually come from, right? How do you get it in the first place? How you get this public key in the first place, so we had these two keys, we had the private key and we had the public key, and they're linked. And actually it does not look as simple as 1, 2, 3, it's a bit a longer thing. Okay, it's a bit a longer thing, and how these two are linked, the private key to the public key, is via a mathematically quite involved thing that's called an elliptic curve. An elliptic curve is basically a one-way function. You put something in and you get something out. You put your private key in and you get your public key out. And this public key, what you get out of here, you cannot go back, right? I cannot know your public key, and I cannot calculate what was actually originally your private key. So it's safe to publish this. It's safe to publish this to the world and everyone can see it. So in this way, we have now every single transaction that has a from and a to, it has a value and has a signature. I can very easily verify now by just looking at the signature and this public key here that, okay, this thing here is actually correct. It's actually broadcasted and not being interfered with in a correct fashion. And only if this is correct and has been incorporated here, it will actually be taken into a block. Okay, so only valid transactions are incorporated into one block of our blockchain. Yeah, so this is basically the output of our elliptic curve from some passwords or some private key. It could be really any sort of secret that you pass in here. Ideally, you don't use something stupid like this, right? Ideally, you want to use something that's really, really long and really complex, because since it's all public, these attack vectors, which we otherwise only consider as a worst case example, could happen at all times, right? So it's basically a public blockchain that is used for financial transactions is basically one big bug bounty, right? Everyone can hunt these things, can try to find out, hey, what was your secret behind this? And then the money is yours. That's really what it is. So we really have to think about security considerations such as these key storage, like where do you actually keep this damn thing? And how do you really interact with it in a quite secure fashion? All right, with this one, we basically finished this first thing here. That was a Bitcoin style blockchain. So very much simplified, but this is basically how Bitcoin works. Okay, so Bitcoin allows us to transact value that is denominated in Bitcoin. That's this value which we have here in our transaction. It's not Swiss franc, it's not euro, it's Bitcoin. And that's all it does, which is pretty big. And it's so big that it was actually suggested for the Nobel Prize. And it had this technicality issue, which is that nobody knows who was the guy who actually did that. That was sad. So didn't get the Nobel Prize. But basically that's what all banks do, right? That's a huge financial system which is based on this premise, and we now have an inherently secure way in a global peer-to-peer system to transfer this value, which is huge, right? It's a multi-billion-dollar industry. So, yeah, but on the other hand, there's this system kind of is devised by people who are more on the nerdy side of things, and they always want more. If you say you can do this, we basically have a hard drive. We have actually a very inefficient hard drive that can only append. We cannot erase stuff, we can only append. We can do this in a not very fast way. That's not exactly where we want to go. So what if we can take this hard drive and kind of upgrade it to be like this machine from hell over here? So we want to do arbitrary things, right? So we don't just want to send money around from A to B. We want to do much more complex interactions between two parties, potentially more parties. And that's where smart contracts come into play. Who here has heard about smart contracts? Yeah? Anybody interacted with any sort of smart contract? One and a half. I'm interested about the half. We can get to it later. So we will change that, by the way. Okay, so how do we get there? And what is this actually? Yeah, so fundamentally, a smart contract, there's a lot of fuss about it, but it's very simple. A program on a blockchain that can control financial assets, not more, not less than that. Okay, it's not a contract like I sign, a contract when I buy a house. I don't need a lawyer for it. I need some mathematics, some IT for it if I really want to understand it, but that's all. It can, however, mimic certain features that we also see in contracts. So we can very much do things that Andre gives me money if something happens, and then I pay it to Meher, and then Meher does something. So these complex relationships we can do, but all we need is software, which is kind of beautiful. We will see what we can do with this. So, how does this work? Let's continue our toy example of our toy blockchain here. So we have, again, the from, the to, and the value. We have this split up in a couple of blocks. Now we use block hashes here. We have some, some proper addresses from where we send transactions. Now, how do we bring in a smart contract here? Well, we add something that we just call payload. We just add an extra column from our Bitcoin style blockchain. Very simplistically speaking, we just add something. And this first something looks very weird, right? So this first thing here, what is this? This is actually the creation, or we also say deployment, of a smart contract. It's basically compiled output, you could say a program for this blockchain that is compiled to run here on this blockchain. And we don't really know what it is, but we'll see some examples. And what it means now, just for simplicity, I changed back to this simple 1, 2, 3 model, okay? That simply means that this 2 here, this recipient here is not a person that receives this money anymore. It's a smart contract. So the smart contract is now, that is defined in this code. So it's just compiled binary code. Is now living at address 2, and it can do things. So what can happen here? What can happen here is that we see address 2 popping up down here again, right? It receives data, and it also receives financial value. So we said it can contain financial value. It doesn't have to. We could also just send data to it. So we send some hello world data, and it can do something with it. And what it specifically does here is actually pretty interesting. So we see the number 2 down here again, right? So what is this? It sends money to its creator. So although we have a program that can take funds, can take data, can have arbitrary logic behind it, it can send stuff around. So we very well can program something that takes data from all you, does something, and then it's a service provider and it pays me, for example, right? Let's say I deployed this contract, so you can mimic that. You can mimic all these things. The next thing is actually, I find even more interesting. You see this number 2 down here, and what happens here is that this contract creates another contract, right? So you can have a very complex interaction between multiple parties, which are either people or smart contracts, okay? And this really, really widens the play field of any sort of financial interactions that we can do significantly. Yes, please.
How do you calculate the address to where you wish to send the contract?
Very good question. Yeah. So now my toy model gets debunked. You actually, when you create a contract, you don't send it a to address because you don't know where, right? So if you create, and now we're getting, so this is just a bit more abstract. Now it gets a bit more specific towards the Ethereum system. So Ethereum is a blockchain which features smart contracts, just like Bitcoin is a blockchain that doesn't feature smart contracts. If you want to create a smart contract or deploy a smart contract, to be accurate, you don't provide a to field. You don't. You leave this blank. And what you get back is actually an address where this contract lives, so to say.
So the Ethereum system creates a new private and public key?
No, it doesn't, because that would mean, then the question would be, what happens to this private key? Who gets the private key? It's kind of tricky, right? Because we said this program here has its funds, right? It is itself in control of funds, and that's something that we really have to wrap our mind around. It's code that is in possession of funds, and there's nothing anybody could possibly do to mess with that code. And that will take a generation of people to change their mind around, only that simple thing. And because that private key would mean somebody can mess with it, right? If there was a private key to a smart contract, it means somebody could mess with it, but there isn't. Okay, so this, whatever this is now in possession of all the funds where we had it too.
But how can I check that the transaction?
This one here?
This one here, for example, in fact, is created by that smart contract.
Yeah. So any sort of contract interaction. So let's say let's start with the easier case. Let's start with the easier case. We send something to a smart contract. We send something to a smart contract means this code here is being executed. So that's all it does. It doesn't ask anyone, hey, could you sign this transaction? It's actually only and only executing this code here, which is standing here. And upon this execution of this code here, it can do further actions. It can, for example, now trigger something that sends money around. But this is all pre-programmed in this code here. Okay? So there is no way of anybody interfering with the assets that are stored behind the code of the smart contract. And you can very well program a financial black hole, if you want to say so, something that only pulls the money. Because, for example, you deployed a smart contract that's empty, that doesn't do anything. It still has an address, it lives there, you can send it money, and it doesn't do anything. It doesn't do anything to an extent that it doesn't even have I'm sorry, send me the money back function, right? If you don't have an I'm sorry, send me the money back function, that money is gone. The Ether are gone. And that happens a lot. Like we see this on the blockchain a lot. That not just like this, but there are many interesting examples of smart contracts getting into deadlock state. So where you have there were some game examples where people were playing around, and then some bug happened, and you were kind of in a locked state. All the funds were stuck in there, and that's it. End of the story. We can all look at it, but we can't interfere with it. Which is also very interesting from a...
Hard fork, yeah.
Sorry?
You can try hard fork.
Yes. But you could basically, the interesting property about that is when you look from a coder's perspective that, there's a bug here and there and we fix it. No, you can't fix it because that stuff here is written and it's carved in stone just like everything else that is on a blockchain, right? So you can have certain functions that allow you to update, but inherently you can make something that doesn't have a I screwed up function, right? That's just there. And that's also another concept, which is, I think, something that we have to wrap our head around when it comes to software development. Mm-hmm.
Are all smart contracts that have been written since inception on the blockchain right now?
You can, yes and no. You see the transactions in the blockchain, yes. But a smart contract can have a self-destruct function. And what the self-destruct function does is that it basically erases itself from the memory. Because this stuff here is written in the memory of all the nodes that run the network, which you could say, hey, that might not make sense, right? So eventually, you can have a function that deletes it. And it's incentivized to delete it. So if you call self-destruct, behind all of that, side note, behind all of that, there is a way to prevent spam. And the way how we prevent spam is that we charge a small fee for every single transaction. And end of the side note, if you come back to the self-destruct, this is incentivized by negative fee. So you get some money back just because you invoke the self-destruct call. And self-destruct kind of frees memory, and it's in everybody's best interest that we do that. So that's the thing here. Good. Okay, so that just kind of gives you a short idea how we incorporate this smart contract in our toy blockchain. And it's really a novelty in all sorts of interactions that we can have, just because payments have been around forever, right? So for me as an engineer, it's kind of sad to see that there have been, this here is actually a claystone in which people were logging the exchange of financial value. And this has been around thousands of years before the invention of the wheel, right? So sorry, accountants were first. And people have been doing it for thousands of years, have been trading money and goods between people and organizations. That's the two fundamental kinds of transactions that have been facilitated. And that was all, right? And now, actually since just over a year, we have a third kind of a transaction, right? And that is to programs. And I'm not talking about programs because you might say, hey, yeah, we can go online and pay on PayPal and stuff like that, right? And I put my credit card there. No, you don't put your credit card details, which allow the program to do a transaction on behalf of you, but the program inherently owns funds, transfers them, and does whatever it wants or somebody else wants it to do with it. And this date here, that's kind of when this started. So that was the Ethereum Genesis block. So that was the time when the first block appeared on this Ethereum network. Mm-hmm.
Why isn't this possible with Bitcoins? Also, I mean, not the smart contracts, but the possibility that programs create their own account and do payments, like part sensors. Also.
Yeah, I mean, you can do that, but fundamentally, you could say I write a program and it is actually running here on this little device where you store some Bitcoin on it, and then it does something, right? When I press a button or something, then it issues a transaction. That's what you mean.
Well, it could autonomously.
It could autonomously do anything.
Buy a parking
Yeah.
car and send Bitcoins to somewhere else.
Yeah, you can do that. You
Energy
can,
or whatever.
you can do that. But you could actually do the same with a credit card, right? You could put a credit card in this thing, load it with something, and
But
it...
the credit card is not legally assigned to the sensor, for example. But Bitcoin address is possible.
Yes, in a way, yes. But still, I could open your device, unscrew like all the stuff, and find a private key in it, and I do it, right? So a Bitcoin transaction is always associated to a private key that controls it under the hood. So you're right, yes, you can do that. You can build something that then signs a transaction upon an event of something else. You can do that, but I can kind of steal it, right? If I take its private key away, then I'm the master, right? And the funds are mine. So here in this way, we write a program that doesn't live inside a box. It lives inside the blockchain. And now Bitcoin allows you to do actually, I mean, I was a bit rude to Bitcoin. I apologize. Bitcoin can do a bit more than the stupid transaction from A to B. It can do certain types of very minimalistic programs as well. That you could do. But you could not do this whole full-blown complexity of Ethereum smart contracts that you can actually develop fairly easily. So that really is the core difference here. Now, the last thing I want to show is gamble for Ether, right? So everybody likes gambling. Gambling is kind of not allowed in all places. So that is one motivation for why gambling on a blockchain is kind of interesting. You could allow gambling anywhere, right? And I heard from Meher that gambling is kind of limited in India. That's correct, right?
Cricket gambling.
Cricket gambling only. Okay, cricket gambling. So we're not going to gamble for cricket, but for Ether, right? So that's one motivation. You can censor it, right? You have this network which is living in this peer-to-peer network, and peer-to-peer networks have to be shown to be really censorship resistant. That's one motivation. But there's more. Another motivation is you can prove that it's not rigged, right? So you can prove that this thing for which we're gambling is going according to the rules of the game, which are known and carved into code, right? So if you see the code, you know what you are doing, okay? So that is one way of proving how this works. And to actually give you a bit of feeling for how this works, we are going to do that. So we prepared some paper wallets. Alright, could you help me maybe with the distribution? Wie viel hast du da? Komm mal. I need one. Hey, okay, there's more. So what we do is we have this is a wallet, okay? And what we see on this wallet is actually an address and a private key, right? So on this address, and we're going to test this address. Sorry?
You have to memorize it yet. No.
Yeah, this is usability is an issue I'm not going to talk about, right?
This one's on top.
Yeah. Ich habe mir noch eins rausgenommen. So, what is this thing, right? So the private key, I told you that's the one you should not show to anyone, right? So I showed you my private key, so this one is compromised, right? Yes. Your address is what you give to other people to send money to. Now, you see this long private key, you also see this long address, but what can we actually do with it? So, I'm actually going to show you how we can walk through using these things. So, the best way is if you run a full Ethereum node. Now, running a full Ethereum node is not something that's very practical. So there are some wallets which are online, but it doesn't mean that you actually send your Ether to some server. It just means that it downloads a JavaScript, and the full implementation, including making the signature, is implemented in JavaScript. So you could go to this Ethereum, so my Ether wallet, and disconnect your computer from the internet, use it to sign a transaction, then take the signed transaction. If you're really afraid of somebody interfering with your things, then you take it to another computer, connect it to the internet, and broadcast it. You broadcast it to the whole network. Now, this is what we're going to do. Okay, so first of all, we're going to check if there's actually anything on this thing here. So you can actually, if you happen to be online, you could open the.
So we downloaded Jack's wallet for Android. So
I would go on my Ether wallet. And I open this QR code reader. And yes, where is it? Here. So, and the first thing I'm going to scan is my address. Okay, so I take this address, and the next thing that we need is actually a thing that's called a blockchain explorer. So since this, since everything is public on a blockchain, since everything is public on a blockchain, we can look in it, right? Okay, so basically what you can do is you can go on Etherscan.io and you can copy paste your address, and in this way you can check if there's any Ether on your wallet. So you can use any sort of QR code reader and upload it. So there's one search box into which you can copy paste your address.
from the Ether wallet.
From the Ether wallet, correct.
Uh-huh.
So I'm basically copying my key here again. Okay, yeah, so what you can do is you can basically scan this code here. Okay, you scan this one, and you find on etherscan.io, you find your balance. And the next thing I would want you to do is, could you scan this QR code? Could you scan it? Does that work from back there? Just to check, because there's another account behind that.
Yeah.
Yeah, it works. Because that's the actual example I wanted to walk you through. So, did you check if there's something on your wallet? Did anybody manage to check?
There's 90 cents on my.
There's 90 cents. How much is it in ETH?
Ether.
.1 Ether. Okay. 0.1 Ether. That's exactly what it is.
Okay.
Sorry, I'm too slow. I don't understand. I went to etherscan.io
Yes.
and put it in my address, which I scanned earlier, and so I copied. And then I get back to my Ether wallet.
Ah, no, sorry. You go on etherscan.io
Yes.
and paste your address in the search box.
Into the search box.
Yes.
Okay, then.
Let me try to see if I can. Okay, now I seem to be online. Okay, etherscan.io, and on top we see a search box into which I'm pasting my address. And I see, and also I have 0.1 Ether here, okay? So on top
For some reason I don't see that go button.
Okay. Maybe just press enter. You can also go on, there's another enter works. There's also another one which you could use. It's called etherchain.org and has the same concept. So you just paste your address and see what you have. Don't send your ether all away, okay? You will need them in a minute. Okay, so next thing that we're going to do is, now we can send this around. And how can we send it around? We can send it around with this My Ether wallet. So you can go on Send Ether and Tokens. And now, that's kind of the alert, right? Now we have to import our private key. So we basically have our private key address. We go back to our QR code reader. I just click on scan again. I'm scanning this private key, which allows me to send transactions. It asks me to unlock the wallet. Also here I see I have a balance of 0.1 Ether, and I can send this around now. Okay, is at least one person in this room this far? Somebody get to this My Ether wallet send transaction? And you should get a screen that looks similar. And also account balance should say something like 0.1.
Yes.
Okay, now the question is, we always want to get more, right? So how can we get more of our Ether? And what I prepared is a little game. Now, unfortunately, most games are a bit complicated in that we have to call some functions and do something that's a bit more involved, for which you need a full node. And the address, which is behind this QR code here, so maybe you can scan this address here. I'll just open it in my blockchain explorer. What is behind this address here is actually kind of interesting. So maybe I'll make it bigger for you, huh? It's also actually on our Twitter, so if you go on Validity Labs Twitter, our latest tweet has the address of this guy inside. And if we look at this one, it's actually pretty interesting. So this is a game, if you believe it or not. And if you are into reading binary bytecode, then you can look at the contract code. So, you can...
It's not binary.
It's hex, yeah, that's correct. It's hex.
I don't get the point.
Okay, and what happens here is that this gambling contract, we can see what happened here. So 2 days and 20 hours ago, somebody played this game. So what happened here is in the first transaction was contract creation. So what we see in this transaction here is, let's look at this transaction here, for example. This was going back to your question, how do you create a contract? Actually, you don't send it to anything, so it doesn't have a to. So it just tells you, okay, something has been created. So we created a smart contract that it was the first time this address has been used. Then there have been 3 transactions of 0.001 Ether. So 0.001 Ether were being sent. And this is people who were signing up to the game. And then they were distributed. So this is kind of gambling. So you can send an Ether, and after 100 seconds, it picks a lucky winner, and that winner gets all the Ether that have been paid in. Okay, so it's a very simplistic example of a game, but for the ones that have interacted with the blockchain, this is a game that only utilizes a default function. So normally, if you make a smart contract call, you need to specify a function. So a smart contract is something like a class, and you call usually a specific function inside this class. Now, there's one specific function that is called a fallback function. Whenever you don't specify a function to be called, it's calling that one. So all the game logic here is implemented in this fallback function.
Yes. What was the Twitter of the with the address of the
Validity Labs. So go on Twitter, Validity Labs, and we are in there. So in there you can find the smart contract address. And you do realize that interacting with smart contracts, although I try to make it simple, is still a bit cumbersome, right?
And the address is the QR code which showed together with
Here.
Yeah. Okay.
Yes, that's the QR codes. So this is the address at which this game is being hosted. What this game does is just short explainer of the rules of the game, okay? So what this game does is I will send some ether. As soon as I send some ether, an internal counter starts. Then everyone who wants to play has 100 seconds to register in the game. And you can send a transaction of 0 ether. A 0 ether transaction is still a valid transaction. So you're basically just telling it, hey, I'm here, sign me up. After 100 seconds, I will send another 0 ether transaction to this address, and it will realize, hey, timer is over, let's find out who's the winner. Then we have this list of subscribed players, so everyone who said, yes, I want a game, is subscribed. Then it will pick one randomly, and that person will receive the ether. Okay? Rules of the game clear? What? Yeah?
So I made 100 addresses and
Yes.
and 0 ethers.
Yes, yes, exactly. So it's a very attackable version of the game. It's attackable in many ways. So it's just a very simple proof of concept of how you can gamble on Ethereum by just using a fallback function. So let's go ahead and let's try this. Did somebody manage to go to put this stuff into my Ether wallet and scan the address of the game or get it from Twitter?
I added the address of the game and I'm about to...
No, don't send yet.
I was telling I'm about to.
Okay, good. Good, because the thing is, I mean, you can go ahead, I can't stop you, right? So it's a free world, right? You can use this thing and I can't stop you even if I wanted to. That's kind of the beauty of it. Okay, so I have now unlocked mine here and I will copy paste the address. So it's this address here. I send you a generous amount of 0.04 ether, and it's just so that we can do it again in case it fails, okay? Okay, everybody ready? Okay, I would suggest that we make a first run of the game, and we tried it already once, okay? So I copy paste now this into the to address. You can do the same thing. And you put amount 0, okay? You don't have to send anything. I mean, you can sponsor the pot, and whoever will win will be happy about that. Okay, so I will go on generate transaction and then I scroll down and I'll click on send transaction. It asks me if I really want that. Okay, so now what happened is that I have this raw transaction, I have this signed transaction, so with the signature, this thing is now being broadcasted to the Ethereum blockchain. If I go back to the smart contract, it takes about 15 seconds to get incorporated, and we see that it was me. I was sending something here, and we had a generous sponsor. So whoever this generous sponsor was sending 0.01 ether. You can leave it blank. Meher was the generous sponsor? Thank you, Meher.
I think I also sent that's
Yeah.
Oh yeah.
Transaction.
Yes.
Okay, many people want to play with us. So what we see here is some transactions. This is live, huh? Now I can't wait. So what we see is that a bunch of transactions, these here, are already in the blockchain. They're incorporated in some block and some are pending. Pending means they have been broadcasted to the network and we're waiting now for this average 14 seconds to get incorporated into a block. So the 100 seconds is ticking.
The 100 seconds is programmed into the contract?
Yeah, the 100 seconds is programmed into the contract.
Can you show the QR?
We see currently our smart contract is in possession of 0.06 Ether because we had a couple of generous sponsors.
Sebastian, can you show the QR code reader again? The same.
This one?
Yes.
It could be that the game is over, but we will
I think
see.
it's over. There's now the balance.
Dann machen wir einen Haken.
Okay, sorry. Then let's stop here. No more sending, right? No more sending. I know I can't stop you from it, but let's see what happens. 0.001. That means the next game already started.
I didn't win. My balance is still.
Okay, who won? Let me see if I won.
Oh, I hope so. So where do I
That would
have
be
to
strange.
go to-
Did we check the code?
So, let me see. I got this amount here. I check my own balance now. So I copy my own code and send it.
Game had moment.
I think I won.
Ja, wie cool ist das Smart Contract?
Okay, just because I won, and I mean that's a bit embarrassing.
Let's
So
try
we
again.
have to play another round, right?
Yeah.
We have to play another round.
Until you
So again, from the beginning, right? So I open my Ether wallet. I go and send transaction. I'll just start from scratch, okay? To do it real slow. So I scan my private key. Yes, you could now basically scan a QR code from my skin and steal all my money. I hope my QR code scanner is faster than yours. I don't see anybody scanning, good.
I'm
So-
assuming not all of your wealth is in that one private.
You can check.
That's true. Yeah.
So I'm taking this private key. I go on myetherwallet.com, send Ether and tokens. I click on private key. I paste it. I click on unlock, and now I have my wallet, right? So I am now rich. I have 0.011 Ether and so on. Now I want to play the game. So if you don't have it, you can get the contract address either here.
So I have a question. Why
Sure.
did my account balance decrease?
Despite sending 0 Ether.
No, even below what I sent.
Because you had to pay for a transaction fee. So everyone has to pay for a transaction fee. Okay, the game is back to 0. Right? So I just copy this address. I didn't start yet.
Are we ready for the second round?
Almost. Almost. So I'm going to send.
Man sieht hier dran, dass das nicht stimmt.
I'm going to send 0.1 Ether. We're going to gamble for 0.1 Ether, okay?
Almost $1. It's very generous.
So I click on ready, steady, go. I generated a transaction.
Yeah, sometimes the generate transaction button doesn't seem to work.
Doesn't it?
Yeah.
Okay. I didn't even send the transaction yet, sorry. So, yes, I'm sure.
Ja, manche Stutzen.
Ja, Handy.
Ich glaube, das jetzt auch.
So we see somebody was faster than me, 0.01.
Suppose that's me.
Okay, my 0.1 Ether are in as well. So and we see them as pending, okay? So you don't see them in the account balance yet because they've not been incorporated in a block. So there's some people that are mining this block. Every 14 seconds there's a new one in average, so sometimes it takes longer. You can actually really put 0. You don't have to put 0.001, you can really put 0. You can also put random numbers.
And I need to get back to etherscan.io to access my wallet, or
No, that's just to inspect anything. That's just to look at what's going on. And now just as my 0.1 Ether has still not been mined. Yes, because it takes a bit longer. Now, the thing is, this game will only get evaluated, so the winner will only get evaluated once it gets another transaction in, right? So after this 100 seconds are over, then we have to make one extra call, for example with 0 balance again, because otherwise it's just lingering around there. And this will then basically evaluate it. Okay, there's one more transaction on pending. Maybe this one will actually already call the winner. The winning.
So doesn't it reset the 100 seconds each time? So much?
No, it doesn't. Only the first time. Yeah, otherwise I could spam it, right? I just, as soon as I see you put a large amount of ether in it, I just send 0 ether transactions every, so we can check it all out. Out of gas. Yeah, what does that mean? That is probably some account which does not have enough ether on it anymore to pay for the amount of gas. So this gas is basically the transaction fee, right? So what we see here is that this account did not have enough ether on it to pay for the gas. Okay, I will give it, I think the timer should be over by now. I will give it now a 0 value transaction to evaluate the winner. Okay, that was just a very short demonstration of how you can interact with a smart contract, okay? How you can really use your private key and address, and how transactions really work. So whenever you were actually sending something to my Ether wallet, what actually happened under the hood was that this was being broadcasted to one node, which then was sending it around.
Worldwide.
So, worldwide, yes, to every single node in the network, including actually this one. So this one is just some web interface wrapped around a node.
I suppose you wrote this contract by yourself.
Yeah.
Maybe could you show up the code,
Yeah.
how it looks like?
Yes, let me look that up. So you find it actually on Validity. You see my screen? Validity Labs /d game. And there is this smart contract in here. So it's very short. It's under 50 lines. I don't say that it's bug proof. It's basically what happens here. We have this function without a name. So forget this payable. Payable means just a function that can take money in. This is a fallback function which gets called every single time nothing else matches. If we don't have any players registered, so players is an array of addresses. Whenever this happens, then we call the new register time and register time. So we just set it to now plus whatever the time is. By default, it's set to 100 seconds. You asked if it's coded, right? It's coded in. We can change it, but it's for now set to 100. Once the time is over and we had some players registered, we find the player, which is just the time now, modulo number of players in the game, which again is of course not very secure, right? Because this now is not a very random number. And eventually what happens here is that the player at index winner receives the entire balance. So that person will receive the entire balance of the smart contract. In the end, we delete all the players, and we can start over again. So that's just what's going on here in this very simple smart contract.
And this code is in the blockchain on every node.
Correct. Not the code, but the compiled version of it.
Yeah, the compiled version.
Yeah.
Will never be deleted.
We can check. I'm doing back practice here. I do not have a self-destruct function here, so yes, this one will remain forever. Yeah.
Forever, ever.
And all the time, every 100 milliseconds, you will do the evaluation for the game.
No, the game will only be evaluated once it receives some payment.
Okay.
So I think this example showed a couple of interesting features of smart contracts. One is that even if I wanted to, I couldn't stop it really, right? I didn't code it in. I can't control any of the funds in there. It goes out to whatever it says in here. Another one is that it's kind of pseudo-anonymous. Once you know my address, you can see everything that happens there. And another thing is they can't trigger things by themselves. They can't say, hey, now send all the money to Andre, because they always have to be triggered. So the initiation of any sort of action always has to come from an external account. External account means one that's controlled with a private key, just like on your paper wallet. So this sort of interaction dynamics is somewhat different than what we know from other programming languages where we have events, right? Where we have some events that trigger something external and then does something else. So we can't do that. We can only react to something that comes as a transaction from the outside.
How do we get the initial 0.1 ether to
Onto the wallet?
Yeah.
We were essentially loading it. You can also see that on the blockchain, by the way. You can see where it came from. So you can make a transfer just here in this one. You can basically make a new paper wallet or any sort of other wallet and send a transaction, right? I can send you the Ether now. So I can send the Ether to you. So you can do this with any method.
So this program is started if one person sends.
Correct.
Where is it? And then it runs 100 seconds. Where?
It's not running for 100 seconds,
Wait.
but it's saying now you have 100 seconds to register to play this game. After 100 seconds, it evaluates who's the winner. So it's not running 100 seconds, then doing something. It's not really running.
But where is it then?
That's a very interesting question. Where are any of these smart contracts? Where do they live, right? These smart contracts are actually, or this bytecode actually, yeah, the bytecode is visible.
There must be one computer somewhere.
No, not one.
No, it's on every single node. So this is the program, right? So this program is stored.
Where is the random?
All miner needs to run it. Every miner needs to.
Every node, not just miners, actually every participant in this Ethereum node, all the machines that we had sketched before, they all have this one on their hard drive now somewhere. So all of them download that, they have that running, and they have this now on their hard drive.
They download it, or it automatically, if you're on the node?
Yeah, so the node downloads it for you, exactly. So you run this program, so here there's the Go Ethereum implementation, it's an Ethereum client. Once you run it, it connects to a bunch of nodes that give me all your blocks. It gives you all the blocks. One block contains one transaction, which contains this, right? So that's how you get it. And the question, where is it, is actually a very good one, but it's everywhere. Every single computer in the network, every single node has this, and every single node is running this program.
The question is the time. If you have a random number, real random number, somewhere it has to
Synchronize?
Yeah, it's not random. So
Yes, this is not random.
it's not random. No, it's kind of random.
Yeah, but
It's
if
kind
you
of
have
random.
a random number, or is it
Random number is actually extremely difficult on a blockchain because every single computer it has to evaluate to the exact same result, right?
Yeah.
So it's an extremely difficult problem.
It's not possible.
It's not quite like that. There are some pretty involved mechanisms how you can produce random numbers with multiple sources of input. If we all send some sort of data but we don't know what each other did, then through multiple iterations we can combine these data such that we get something that's pretty random.
You take a private key.
Ideally,
Some private.
yeah, some private data, yeah, some random data actually. Yeah.
There must be one instance that says I am the master.
No, there's no such thing. That is exactly the concept. That's exactly the concept which we try to avoid. You can of course program that. You can say, hey, this account here is the master, right? This one says what is random. You can do that. You can say, hey, that is the provider of a random number, and you could charge for that also. So it provides sort of new ways of how we really can deploy services. So, and it goes really for the whole scale. It goes from, you can say, hey, Andre is really good with random numbers. Andre is a random number source. You could also say he's really good with insurances, right? He provides you some sort of data feed on some sort of insurances. So any such services which are very centralized, you can provide in this decentralized world very well. That does work, right? If it's kind of...
But you have to trust.
Sorry?
But you have to trust them.
Yeah, right. And I mean, then you have to come up with concept, okay, how do we make this good, right? Because maybe Andre is not a good source. Maybe Andre wants to sleep when I want to play, right? So what do you do then, right? And all these sort of things we have to factor into the kind of solution design that we're talking about then. Yeah.
Is the size of these programs restricted?
Go on.
How large can these programs become?
It can be, so first, large can have two meanings, right? Large can be how much source code can be behind it.
Or
It can
binary
be
code
pretty
is more
big.
interesting. and
Or
quantile.
computationally intensive, right? So how much computation can you run on it? And you can actually run arbitrary computations on it as long as you pay for the transactions for it, right? Because if you look into our smart contract now, you see that there were these transactions here, and you see that these transactions cost gas, right? So this is the transaction that we pay for it. And you see that the more complex ones actually cost more. So, for example, the last one here costed the most, right? Yeah, this one was also a bit expensive. And the reason is, this was more expensive probably because they had to evaluate who was the winner, I assume. No, which one? No, actually not. This one here, right? This one.
So are there some amount of ether converted into gas?
Yeah, so that's just what happens here. So you pay for these transactions in Ether. So if you look at the transaction, you don't only have the value, you also have a fee that is associated to every single transaction.
Yeah, so there is an upper limit to
Which you can afford.
computational time or to the computational energy or whatever,
Correct.
but what about the size? I mean, when
yeah.
I have some gigabyte
Yeah,
as a binary code.
So what, for example, you upload your movie database here, right? The limiting factor is that you don't only pay for computational cycles, you also pay for data that you send. So every byte that you send has a certain fee associated with it, so that effectively economically limits the amount of data that you can send into it.
What me concerns about this all this blockchain technology, which is worldwide used, not the simple island solutions, is how does it scale? I cannot imagine that this really scales if you have to put it to every node. This is exponential growth.
Yeah.
And I think Bitcoin might have some problems if everybody would use it.
It does have some problems right now, actually. As we
Where
speak.
will you store all these things? And
Yeah.
so with Ethereum, if it's
It's a
really
similar.
used,
So
not just-
I mean, scaling is it's admittedly one key issue of blockchains.
Yeah.
There are some solutions for it. So there are blockchains. So in Bitcoin, you can run approximately 3 transactions a second. On Ethereum, this goes up to approximately 25 transactions per second, depending on what, right? So depending on a really complex or whatever you do. But roughly, you can do 25 a second.
In the whole blockchain?
Yeah.
Okay.
So 25 transactions per second that are
World.
worldwide.
Yeah, but imagine in the Internet of Things world.
Right, we're talking about
you
different
have
things.
Billions of sensors doing things all the time.
So there are blockchains. There's one, and there was a meetup.
ChainDB.
Yeah, there was a meetup on Tuesday, right?
So that's exactly the point. So basically what they're doing is they're using it for IoT, so in the energy business where you have, for example, meter readings, and you have this amount of readings per second. I can't remember exactly the numbers, but they do millions of transactions.
Yeah. So they did some AWS instances which they had across the globe, and they could go to a consistent load of over a million transactions a second.
It's Visa style.
I mean, Visa style is low, right? I mean, Visa is a small network. Visa has 1,000 transactions a second. So a large network is, for example, YouTube or Netflix. So Netflix has a constant write load of approximately 1 million transactions a second. And that's, that's 3 orders larger than Visa. So yeah, I mean, Visa, So there are things which are significantly bigger than financial networks that work very well. Because, when I go to Netflix, I can see that movie. And BigChainDB took on that to say, okay, to prove that you can take blockchains to something that scales. Ethereum itself has a different design. It does not scale to that yet. People are working towards something that scales better. but we're not there yet. I think it will take approximately, the timeline will be 2-3 years until this goes to a higher.
By the way, you will never find anything that will scale because scale is arbitrary, so it will always be under limit soon as you use it properly.
Yeah, but Ethereum says I'm the world computer.
Yeah.
So
Can't build YouTube on Ethereum quite yet.
It depends on the use case, I guess. So I guess it depends very much on what specifically you want to use it for, and then finding a solution for that, because maybe it is not required that actually your Internet of Things is broadcasting everything in this thing, which is geared towards censorship resistant, time stamping, and this extreme level of security that it provides. Maybe you don't need it for all the data. That's kind of the... Maybe we go for discussions and close this session for now. I would just like to thank our host here again, and I think we can have some questions.
Cool. Thank you, Sebastian.